Hello everyone and welcome to Lab Manager On Demand. These webinars are designed to discuss a variety of topics of interest to laboratory professionals and connect them with the latest tools, techniques, and technologies. Today's discussion focuses on managing laboratory air quality with chemical fume hoods, and I'm very pleased to introduce our speaker, Beth Mankemeyer. Beth is the sales engineer for chemical fume hoods at Labconco Corporation. Before joining Labconco, she was a business development manager at Ruskin Company, where she focused on the manufacture of louvers for the HVAC industry and architectural products for building envelope applications. Beth received her Bachelor of Science degree in marketing from the University of Kansas and her MBA from the University of St. Mary. She is a certified construction documents technologist and a lead green associate. She's been with Labconco since 2013. Beth, thank you for joining us today.
Hello, everyone. I want to thank you for joining my webinar today on managing lab air with chemical fume hoods, where we're going to discuss ducted fume hoods, some different mechanical systems, and perks of high-performance hoods. My name is Beth Mankemeyer, and if you have any questions about this subject matter, please feel free to email me at bmankemeyer@labconco.com. So without further ado, let's get started. Here's our agenda for this webinar. First, we're going to make sure we're all on the same page and discuss components of a fume hood and how a fume hood works. And after we have that settled, we'll talk about some different fume hoods and different mechanical systems. And then we'll finish up by talking about fume hood performance and a little bit about placement. So to start things off, here are the components of a fume hood. This image shows a typical fume hood exhaust system when tied to a remote blower. Sometimes I get phone calls where people assume a blower comes attached to the fume hood, and that's a scenario we call a built-in blower or an integral blower, and that's not necessarily the case. Some people are kind of surprised by that. So if you're looking at purchasing a fume hood, look at where the blower is going to be located and specify. And keep in mind that built-in blowers are not a one-size-fits-all solution. Blowers have to be sized for the duct run, and therefore you always want to verify the blower is appropriate for your duct run before you purchase it. Also, if the blower is built-in, meaning it is sitting right on top of the fume hood, the ductwork will be under positive pressure, meaning that blower will be pushing the air up from where the blower is located. And that means if you have a leak in your ductwork, that contaminated air will be pushed out of the duct at that location. So a remote blower is always a fail-safe since the duct run will be under negative pressure the whole time. The components of the hood start with the base cabinet or a base stand. In this diagram, we have a cabinet where you might be storing chemicals or equipment or something of that nature. Then on top of the cabinet is a work surface, and on top of that is the main event, the fume hood. Then we've got the ductwork connecting the hood to the blower, and after the blower, you will have some sort of exhaust termination. And per the ANSI Z9.5 standard, it needs to terminate 10 feet above adjacent roof lines, and it needs to be in a vertical up direction, so those vapors will be carried away in the trade winds. So now we have our fume hood set in place, completely installed, and we want to get it up and running. Here's how a fume hood actually works. The room air is going to be pulled through a fume hood via the blower and exhausted outside. We measure that air that is exhausted in a few different ways. First, there is the volumetric flow of air. Basically, we are going to take an amount of air and pull it through the fume hood opening and vent it outside. The volumetric flow is typically measured in cubic feet per minute, or CFM for short. You'll hear CFM whenever you talk about HVAC or air movement. It's just saying that we're taking a cubic foot of space and we're filling it with air and seeing how many of those move in a minute. Because remember, just because you can't see the air, you can have too much in a room, you can have too little, or if it's balanced, you can have just the right amount. A room can be starved of air, and then your hood won't be able to contain. This is very important because when you have a fume hood, you need to put makeup air into the room so that it can pull that air out and stay balanced. So the other measurement we look at is the speed of the air going through the front of the fume hood, and we call that the face velocity. The Depending on how much air you're putting through that front opening, that will determine face velocity. I like to compare this to water because it's a simple example that everyone can relate to. When you're watering some flowers, but the water from your garden hose isn't reaching the ones in the back of the yard, you put your thumb over the end of the hose and the water sprays farther. And it does this because the speed of the water increases. It's not more water. The volume of the water does not increase. It's the exact same amount of water through a smaller opening. Also, within that relationship, if you turn the water up within the same opening, the velocity will increase. Same thing with a fume hood. The more air you put through the fume hood, the faster the face velocity, and also when you shut the sash, the same amount of air will move faster. We can measure face velocity, or the speed of that air, taking a thermal anemometer, or you might hear a hot wire anemometer, and placing the probe end in the plane of the sash. The sash is the glass window that moves up and down on a fume hood. The anemometer measures the speed of the air entering that space, and it typically measures that in feet per minute, or FPM for short. Most fume hoods operate between 60 and 100 feet per minute, face velocity. Pay attention to manufacturers' published data on this because some fume hoods cannot be operated at lower face velocities, and some are high performance and do really well. But I just urge you to be a consumer on that and do your research about test data and test reports and make sure the hood can operate at lower levels. So now we've picked out our hood and we know the air that will be exhausted from the fume hood will be replaced by the supply air, but we have a choice of what type of mechanical system we want to put this hood on. The two choices I'm going to talk about today are a constant air volume system and a variable air volume system. You may hear these referred to as CAV and VAV. These refer to the volumetric flow, or CFM, that we just discussed. The constant volume system has the same amount of air going through the hood regardless of the sash position. So going back to the garden hose example, when you close the sash, the face velocity, or the speed of the air, is going to increase as you close the sash since you are putting the same amount of air through a smaller opening. The hood has bypass areas to assist so the air doesn't go too fast. However, it is still going through the path of least resistance and will enter through the sash opening unless the sash is closed. These types of setup are best for smaller labs. Maybe the lab isn't being used all the time, so for labs with minimal use, or specialty application hoods where you don't want the face velocity to change. The other type of mechanical system that I'll be discussing a little more in depth is the variable air volume system, which means the amount of air varies depending on the sash position. The reason for these systems is to save energy while the hood is not in use. Many hoods are used all day, every day. And since fume hoods are such huge energy hogs, a lot of users want to minimize the amount of air they exhaust. So this system is typically set up with supply and exhaust controls so that you get maximum energy savings of the whole system by varying the volumetric flow based upon the sash position. These systems are best for large labs or general chemistry labs where the fume hoods are running all the time. And these systems usually feature a lot of automation. There are sensors that can be placed on fume hoods so that when it doesn't sense movement after a while, the sash will close and then automatically lower the volumetric flow and result in a lot of savings when the hood isn't in use. So these will have a larger upstart cost, but most likely save you a lot in the long run. And regardless of which mechanical system you have, either of these can and should be used to assist with lab air changes. Here's another view of the VAV setup, and this is a section view of a fume hood on a VAV system. The left image is showing the sash fully open, and the right image is showing the sash fully closed. VAV hoods can change the exhaust volume using some different methods, one being a damper or valve in the exhaust duct that opens and closes based on sash position, which is the option that's shown on this image in the ductwork above the fume hood, or they might have a blower that actually changes speed to meet their air volume demands. Another component that I want to point out as something you'll see on a VAV modified fume hood is a restricted bypass shown on this slide. That is there to ensure adequate face velocity at all sash positions. The latest fume hood designs feature high-performance fume hoods. You may also hear these types of fume hoods called low flow, high efficiency, low velocity. They all mean the same thing, and that's that they require less air than a traditional fume hood. There are only so many hoods that can call themselves a high-performance fume hood, so I'll explain how they're tested and how they earn that title. First, I'll go over the industry standard containment test for fume hoods called the ASHRAE 110 test. It's a three-part test that does a face velocity profile, measuring the face velocity about every square foot to look for a uniform face velocity across the entire face of the fume hood. Then the second part is a smoke visualization test, and that shows how the air interacts with the fume hood. The smoke is a great tool to allow people to see the air and what it's doing in and around the fume hood. Then there's the containment test, the third part, where a tracer gas is used to see how much can be traced within the breathing zone. In order to see this result, a mannequin is placed in front of a fume hood with a sensor in their breathing zone, which is a very important part of this test since air interacts differently in front of an empty hood versus having a person standing in front of the hood. The air actually hugs around a person and creates eddies or turbulence around a person. So it's more of a challenge when we put the mannequin there. And in the test lab, we're able to set the face velocity to whatever point we want. So typically the tests are performed at 100 feet per minute face velocity, then 80 feet per minute, then 60 feet per minute, as that's the lowest operating airflow that's allowed in a laboratory. And that's stated in standards like OSHA, CIFA, and the Industrial Ventilation Manual of Recommended Practices. CIFA is the Scientific Equipment and Furniture Association, and they're an organization that created the definition of a high-performance fume hood. The definition is that the fume hood was put through this ASHRAE 110 containment test, operating at 60 feet per minute face velocity with the sash fully open, which means a minimum of 25 inches open, and on average, less than 0.05 parts per million of the tracer gas was detected in an as-manufactured test. So there's really three parts of this, that it has to be 60 feet per minute, sash fully open, and on average, less than 0.05 parts per million were detected in the as-manufactured test. As manufactured means it was tested by the manufacturer right off the assembly line in the test lab. So if this test was actually done in the field as installed or as used, those are two other parts of the test that can be done, it allows an average of 0.1 parts per million of the tracer gas to be detected with the same sash position and face velocity setup. So keep in mind, manufacturers that say their hoods are high performance should have the test reports to back that information up. So once again, I challenge you as a consumer to ask for these test reports. Know what you're getting and don't be fooled by marketing, because CIFA itself states the following. Note, low flow hoods which achieve a reduction in volumetric flow by restricting the sash opening area do not qualify as low velocity or high performance fume hoods unless they also meet the performance requirements listed above through the maximum sash opening. The maximum sash opening shall be considered a vertical sash opening not less than 25 inches high off the fume hood work surface. That was a quote from CIFA. And it basically states that sometimes you may see a fume hood that can operate at 60 feet per minute face velocity, but that's not a high-performance hood unless it was tested with the sash fully open. So if the published data only shows 60 feet per minute, but the sash opening is 18 inches or less, that is not a high-performance hood because the challenge comes from having the sash raised above the breathing zone. So This doesn't mean the fume hood can't operate with the sash down at 18 inches, but in order to call itself a high-performance fume hood, it needs to pass the test with the sash fully open. Okay, so here's the good part, where we're going to talk about saving money with a high-performance fume hood. And before I even get into numbers, I want to make sure we all agree that the most amount of savings you'll see on a fume hood is if you use a high-performance fume hood along with a VAV system. That's where you're going to see the most savings. Because when the sash is closed, the volumetric flow will go down, and that is where you see the energy savings. So when we talk about these numbers, we will just refer to a constant volume system to keep everything on an even playing field. So here we have a typical 6-foot fume hood that requires 1100 CFM to exhaust on the left-hand side there. This means the fume hood's operating at 100 feet per minute face velocity with the sash fully open. If this exhausts all day, every day, it will cost about $8,800 per year just in energy costs. $8,800 per year. This is going off of $8 per CFM per year, which is a good industry average, but obviously if you're in a place where energy costs are higher, like the Northeast, then that number is actually going to be higher, and vice versa. So in that same lab, using a high-performance fume hood operating at 60 feet per minute with the sash at an 18-inch working height, which is the lowest operational point for volumetric flow, or CFM, it will only cost $3,600 per year in energy costs. So just operating at that point, leaving the hood on all day, every day, is going to save you $5,200. That's a huge number, and that could pay for the hood assembly in a year or two. So keep in mind, this is for optimal savings. You're going from 100 feet per minute to 60 feet per minute. So on the next slide, we're going to look at this a little bit more conservatively even. Here's the conservative approach. So let's say that your safety officer wants to require 100 feet per minute at an 18-inch sash height. We still get to save money because at this operational point, the hood requires 700 CFM, which using the $8 per CFM per year, again, equals $5,600 each year in energy costs. So that's how much the high-performance fume hood is going to cost. But compared to the original hood that cost $8,800 per year to operate, that equals an annual energy cost savings of $3,200. Once again, this is just one hood. If your lab has more than one hood, look at what it could save in energy costs just to lower the CFM. If you have 3 hoods in your lab, you'd be saving about $10,000 per year, and that's on the conservative approach. So you can see it doesn't take a lot to see a return on investment for these hoods, and that is just talking about the exhaust requirements. That doesn't even go into the savings from having a smaller air handling unit because the CFM requirement is less. On the supply side, it really adds up quickly. So if you are designing a new lab or if you want to replace a fume hood, I always recommend to look at high performance if you use your hood on a regular basis. Here I want to talk about fume hood placement a little to show the synergy that's created between fume hood performance and placement. This is extremely important because lab conditions are probably the #1 reason that a fume hood doesn't perform the way you expect. In determining the amount of space necessary for the lab, a layout of all lab equipment needs to be made. So locate the fume hood away from high traffic hallways, supply air cross drafts, or any other equipment that could disrupt containment, such as a biosafety cabinet. Also, on a side note, if possible, the hood sidewall should be at least 1 foot away from the room wall to allow access to service connections for future maintenance. Any kind of cross draft is going to work against the air entering the hood in a smooth fashion. And the smoother the air enters the hood, the better it is going to contain. So that is very important to a fume hood. If you have supply air registers that have air pointed right at a fume hood, block off the area that is facing the fume hood. It's as easy as that. Don't put your fume hood next to the hallway. Don't open any windows in the lab. Don't work quickly in your hood. You yourself could create a cross draft. Don't open and close the sash quickly. All of these things help with fume hood containment. And what does that help? Your safety. And that's why we're all here, for your safety. So remember, if the lab has proper ventilation and minimized cross drafts, then a high-performance fume hood should have no problem operating at 60 feet per minute with the sash fully open. It should pass all the ASHRAE containment tests and will be able to save so much money and energy costs at the end of the day that the hood will pay for itself. Okay, everybody, we've made it. I hope you've enjoyed this webinar and hopefully you've learned a thing or two. If you have any questions at all, please feel free to email me at bmankemeyer@labconco.com. And thanks so much for spending some of your valuable time with me today. I hope you're able to take some of this new knowledge and apply it to your lab. Have a great rest of your day. Thank you.
Thank you very much for your presentation, Beth. Please note that Beth has kindly provided several additional resources that are available to download, and please feel free to reach out with any questions or comments you may have through the comment box located at the bottom right-hand side of your screen. On behalf of Lab Manager, I'd like to thank Beth Mankemeyer for all her hard work and Labconco Corporation for supporting this Lab Manager on-demand presentation. For more information on Lab Manager webinars or to find out more about the latest laboratory tools and technologies, please visit our website at www.labmanager.com. Thank you and enjoy your day.